Hi, Ethan.
There, it's official. All right, so we'll give this a shot. Hey, Ethan. Yes, I did not record while we went over the problems. Ha! All right.
Sucks. Hope you get sunburned.
Wow. That is a little rude. He's relaxing on the beach.
I don't feel that bad.
He's drinking something with a little umbrella,
Yeah.
you know, and we're here in the cold. It's going to make it up to 50 though this week. We hope. Oh yeah, it's going to be awesome. All right. Calculating the field from the potential. Oh, sorry. I'm going backwards. Calculating the potential from the field. All right. So a second ago we said, well, look, if the field is uniform, calculating the potential is really easy because it's just the field times the distance over which we're going to move our point charge. So uniform field, and we're going to use uniform field a lot because the next half of this unit is going to be about capacitors. And capacitors are basically two plates that have opposite charges, and you know that between the plates you got a uniform field. So the voltage, potential difference, is just the E field between the plates times the distance between the plates. That's it. E times D or E times delta X. Unfortunately, it's not always the case. So what we're going to do is derive this for the general case where the field is non-uniform. So imagine we've got, you know, some crazy janky field doing some interesting stuff. And I'm going to take a charge, Ralph, and I'm going to move him in that field. Okay? Remember, the work done on him by the field equals the negative of the potential difference between those 2 points. So, I'm going to say, look, work done by the field equals negative delta U. And the work done, as we go from this point to this point, we can find by just saying, oh, it's the force dot delta X. Now here's the problem. The E field is changing as we go. So that means as we move this guy along, the force is going to change. If the force changes, we have to quick say, oh, Miss Stoughton, we need you, or at least the tools you provide, and we're going to say work is the integral from x naught to x final, which means that the potential, the difference in potential energy is going to be the negative of that work done by the field from x naught to x final. Okay? So, using the wonders of calculus, we're going to say, imagine that from here to here, the field is pretty much stays the same because that distance is so tiny, dx. And if the force then stays the same, we can break this up into an infinite number of little tiny distances and find the total work done, slap a negative sign on it, we find the change in potential energy. Now, of course, as was pointed out earlier, E equals F over Q. Therefore, F equals E times Q. So let's do that. So there's our calculus equation for the change in potential energy. How can I change that equation into the change of potential? In other words, I want the potential difference equation. What's that going to look like? Yeah, drop the q's. So if I divide both sides by q, by definition, I have delta V equals negative x naught to x final E delta x. Okay? Because remember, delta V equals delta U divided by Q. And so what we just did is just proved what we said earlier while we were doing the problem set. If E is constant, we don't need this integral, do we? It just becomes E times X. So if we've got a constant electric field, if the little lines are parallel, E times X. So there you go, Ethan. Now you know how to do all the problems in that assignment 2, 3, 5, and 6 that we just went over, because the secret is E times X equals delta V if the field is constant. All right. Now, delta V is all nice and good, especially when you do it in circuits. Difference in potential, or potential difference, or the change in the voltage, we sometimes call it, is really useful. But we actually want to know what V is, not delta V. What is the actual potential at a particular spot in the field? I say, right there, what's the potential? Now, in order to get the actual potential instead of the change in the potential, what we have to do is make an assumption about our initial position. So if V equals 0 at x naught, then we can drop this delta and just say V. Okay.
You just change it to 0 for x naught.
But where would we have to be in order for the potential to be 0? Say that louder. Infinity. So, if, for example, I've got a point charge here, call him Q. He's making field lines that go out like this. They're definitely not parallel. Okay? In fact, we said that the field intensity is equal to KQ over R squared. Or your book would say it's Q over 4 pi epsilon naught R squared. Either one's fine. If you like the K on top, that's cool. If you want the 4 pi epsilon naught on the bottom, that's cool too. The 4 pi epsilon naught is really helpful in Gauss's law. And we say, okay, as we go further and further from this point charge, it decreases with R squared. So we can't use any shortcuts. And I could find out what the potential is, like right there, by setting up my integral and saying that the potential at infinity is 0. So in other words, walk to the mall, and if I put Ralph at the mall, somewhere in Barnes & Noble at the mall, he basically says, no, it's too far away. Of course, infinity would be much further than the mall, but you know what I mean. So here's how we're going to do it. So let's say I'm going to start this little guy some distance r away, this little Ralphie, and I'm going to let r go to infinity. Okay? So I'm going to say, I'm going to figure out what the potential there is by saying my final potential is 0. So I'm kind of changing the rules just a little bit, but that's okay. So I'm going to say, look, delta V, or V, is negative from R to infinity. And then we'll just say E dr. Now I know I said dx earlier, but we're just kind of moving radially away from this guy. So it doesn't have to be the x-axis. It can be the y-axis or the z-axis. So I'm just going to call it dr. So this is not a really tough integral. We're going to say, okay, well then delta V is equal to negative from R to infinity KQ over R squared dr. And we're going to stick big R in, we're going to stick infinity in there, and all will be good. Before you take an integral, let's pull the constants out. What are my constants?
Okay.
Yep. And?
Q.
Yeah, that charge sitting there, that's not Ralph I'm talking about. That's actually the charge that's causing this field. So he's going to stay constant. I'm going to say negative KQ integral of R to the negative 2 dr from R to infinity. So when I integrate R to the negative 2, I get negative 1 over R. Whoops. There we go. So delta V is V final minus V initial. This is negative KQ. I'm going to have a negative 1 over infinity minus a minus 1 over R. Now, if my final position is infinity, then we're going to define that to be 0. So if we drop the negative signs, we're going to have V naught equals negative KQ over R. So actually, we can drop the naught too. So we can say, all right, the potential at any distance from a point charge is that, negative KQ over R. Okay? Or if you like, it could be, all right, Mr. Everly messed up.
There's signs, sir?
Nope.
Is he divided
Because
by
I just
the
said I got rid of the negative signs. Sorry, Ethan.
I didn't want to say.
Oh, you are such a good person. There we go. I did exactly the same thing last hour, too. It's just, I don't know. A little more sleep. Sorry. My motto is fake it till you make it, right? Okay. Question for you, my students. Now that you've made it through this derivation. Is potential a vector or a scalar?
Scalar.
It's a scalar. Its saving grace is that it's a scalar. So, if you're calculating the potential, knowing the electric field around this guy, what you found at a certain spot, pick a spot, a distance r away, is this thing called its potential relative to infinity. Now, if that seems kind of abstract, but the good news is it's not a vector. Because if you've got a whole bunch of charges, let's say you got, like charge 1, I think the board has died. Let's try this again. Woo! All right. I did something. I'm not sure what I did. Huh.
Oh, you erased something a second ago.
Yeah, I know. I erased it, but then it didn't come back, which is weird. Okay. Anyways, so suppose I've got like a charge here, and a charge here, and a charge over here. Let's make him negative just for fun. And I say, find the E field right there at that little dot. Point P, whatever. The book always calls that point P. You'd say, well, the E field due to Q1 is kind of pointing this way. The E field due to Q2 is pointing this way. The E field due to Q3 is this way. And I can calculate those E fields. And then I got to do I hat, J hat, add them up like vectors. Painful, right? Guess what? If I say find the potential at point P, we don't care about direction. So all we have to know is these distances, call them R1, R2, and R3, and we're going to add them up. We're going to say, okay, it's going to be KQ over R added up from I equals 1 to n. And again, you can pull the K out if you want. It just becomes Q over R plus Q over R plus Q over R. And the minus sign matters because the potential due to a negative sign is going to be opposite the potential due to a positive sign, a positive charge, I mean. And that's all you have to do. This provides us with a whole host of shortcuts, too. So what if I've got the situation where I say, find the potential here, and I've got 3 charges, and this is, R equals 1 meter, R equals 1 meter, R equals 1 meter. So I've got, charge, charge, charge. If all those guys are the same distance away, I can also pull out the R. And it becomes K over R, Q plus, you just add them all up. You just add up the charges and treat it like one charge. Later on, you're going to see problems where they do this. They say, okay, I've got this wire or a rod that's bent into a circular curve, and it's got a charge Q on it. And at the center of the curve, I'd like to know what is the potential right here. Now remember, when we did this for E fields, if I said find the E field there, we had to do some major calculus. You remember that? It was very sucky. But since we don't care about direction, we can say, look, the distance of this charge is the same from that point as this little piece of charge as this little piece of charge. So all we do is take this whole thing and stick it in and say, all right, it's KQ over R. As long as all the charge is the same distance away, just treat it like one charge. It becomes a point charge as far as V is concerned. Okay? So, the calculations are a lot simpler. V is a weird concept. Okay? I took my time last week trying to explain it, and hopefully it made some sense. But the good news is it's a lot easier to calculate than E. So let's do one example, and then we'll call it a day. And let's see if I can. First, I got to erase. Then I want to do this. Oh, look, that's amazing. The example is on the board. So I'm going to switch to draw mode here for a sec, and then kind of slide this out of the way. There we go. So the question is, I got an equilateral triangle of side 5 centimeters. There's a charge at each vertex. I'd like to know what is the potential right there. I should have seen a little circle go, come on. Some days, let's try that again. Draw mode. Now, when it blinks 3 times, you know it actually did it. Okay. So we're going to say, okay, I'm going to pull out the K. We've got Q over R from I equals 1 to n, and there's 3 of them. Okay? So from point P to this guy is like 0.025 meters. This distance here is 0.05 meters. Got to switch from centimeters. And we know what the charges are. He's -8 microcoulombs, +5 microcoulombs, and +10 microcoulombs. Now again, because Q1 and Q2 are the same distance away, we could just say, oh, there's 15 microcoulombs of charge that distance away. So K is like 8.99 times 10. It's basically 9 times 10 to the 9th. Okay. okay, then we're going to say, well, I've got 15 times 10 to the minus 6 coulombs sitting here at 0.025 meters. Do not square the bottom.
Wait, where did that 8.9 come from?
That's K.
Oh, okay.
Yeah, if you want 1 over 4 pi epsilon naught, we can do that too. And then the other guy is located this distance away, which, because it's an equilateral triangle, we can claim it's 0.025 times the square root of 3, right? So we'll do, all right, he's negative 8 times 10 to the minus 6 coulombs divided by 0.025 times the square root of 3, whatever the heck that is. And we've got it. All right? So not a terrible thing. So if you want to punch that out just for kicks and giggles, you don't have to. But that basically takes us through finding the potential due to an array of charges. Sir?
Was 1 5 microfarads, 15?
These, you add them together.
Oh, I added them together because I could, notice if I have 5 times 10 to the minus 6 over 0.025 plus 10 times 10 to the minus 6 over 0.025, they've got a common denominator. So, I just skipped that step and put them together. They're the same distance from our point P. Excellent question. All right. So that kind of wraps it up for today. The assignment is only 5 problems long, 12, 14, 18, 23, and 26 from chapter 24. You got that, Ethan, while you're on the beach? 12, 14, 18, 23, 26. He's actually probably on the way home. But, we'll give him crap anyway when he gets back.
The challenge problem is due tomorrow, right?
Challenge problem due tomorrow, yes.
Do I have a challenge problem?
Absolutely.
I need one right